In the modern world, many things like smartphones, wireless headphones, and electric cars all use batteries for electricity. Batteries produce electricity by releasing stored electric potential energy through chemical reactions. It took us a long time to invent things that could store electric potential energy for our use. The history goes back to 600 BCE Greece, when Thales of Miletus observed that rubbing amber with fur would make the amber attract lightweight objects. From 600 BCE until the 1600s, this was a common discovery that many people made but didn't recognize as electric potential energy. In 1785, Charles de Coulomb created Coulomb's law, which describes the forces between charges and created a basis for electric potential energy. In the 1800s, Carl Gauss and Michael Faraday started developing field theories, and the idea of electric fields storing potential energy started to form. In the 1860s, James Maxwell Clerk combined the ideas of electricity and magnetism into Maxwell's equations and proved that electric fields did in fact store potential energy. But what is electric potential energy? Electric potential energy is the amount of energy in a charge at a distance away from the source of an electric field. Electric potential energy is the energy you would need to move a charge against an electric field. The further you move the charge against the field, the more energy you're required to put in. You would also be required to put in more energy to move the charge through a stronger field. It is similar to how a car at the top of a hill has gravitational potential energy due to its height. Here we have 4 diagrams showing the force electrostatic on different charged particles within electric fields. In scenario 1, the force electrostatic on the positive particle is going towards the negative charge in the center, and the force electrostatic on the negative charge in the top is going away from the negative charge in the middle. This is because like charges repel and opposite charges attract. In scenario 2, we are applying a force on the positive charge in the opposite direction of force electrostatic. This is increasing the potential energy of the positive charge. In scenario 3, we see that the positive charge in the bottom right corner is further away, and this works similarly to gravity, where the higher you raise an object, the more potential energy it has. So the further you move a charge away, the more potential energy it has. And then we have a larger charge in the top corner. The larger charge is supposed to represent a higher magnitude charge. So it also works the same as mass does in gravity, where the higher mass you have, the more energy it takes to lift it up. The stronger charge you have, the more energy is required to move it away from another charge. In scenario 4, we have a positive charge in the center instead of a negative one, and we see that the force electrostatic on positive and negative charges swaps direction. On the positive charge, the force electrostatic goes away from the positive charge in the middle, which means we have to apply a force towards the charge in the middle to increase the electric potential energy. And the negative charge, the electrostatic force is going towards the positive charge in the middle, so we have to apply a force away from the middle to increase its electric potential energy. Electric potential energy is equal to K times Q1 times Q2 divided by R, and we have change in electric potential energy is equal to Q times change in voltage. We've already talked about the first formula a little bit, but it is used to find the potential energy of point charges within electric fields. A point charge is a concept in physics where we treat an electric charge as if it doesn't have any volume. Treating the charge like this makes it much easier to calculate electric fields and potential energy. Because point charges are so small, when finding the radius, you will just use the distance that the two charges are away from each other. In this formula, we have 5 variables: EP, or electric potential energy, K, Q1, Q2, and R. The K is Coulomb's constant, which is always equal to 9.00 times 10 to the 9. The Q's represent the magnitudes of the two charges we are dealing with, and R is the radius, or as we discussed earlier, the distance between the two charges. If we look at the signs on our charges, we will be able to tell whether our answer will be positive or negative. If both charges have the same sign, our answer will be positive because they will repel each other, and it will be negative if the signs are opposite and they will attract each other. change in electric potential energy is equal to Q times change in voltage is used when calculating the potential energy of a charge located between parallel plates. Parallel plates are two plates at a set distance apart that have different voltages applied to them, which causes one to develop a positive charge and the other to develop a negative charge. Because of the opposite charges on the plates, the positive charges on the positive plate will accumulate on the inner surface of the positive plate, and the negative charges will accumulate on the inner surface of the negative plate. The accumulation of opposite charges on the inner surfaces of the plates will form a uniform electric field between the plates, directed from the positive plate towards the negative one. And the greater the difference in voltages is between the plates, the stronger the electric field will become. In this formula, we have 5 variables. Change in electric potential energy, which turns into electric potential energy initial and electric potential energy final, Q, Vf, and Vi. Q is the magnitude of the charge that is between the parallel plates. Vi is the voltage of the plate that the charge is touching at the beginning of the question, and Vf is the voltage of the plate that the charge is touching at the end of the question.
Now we're going to do a sin question. The question is, at what speed will a proton that is initially at rest hit the plate on the right? So this is a question using parallel plates, and our proton is starting here on the left plate, and it's going to be attracted towards the right plate, and we want to know how fast it's going when it hits the plate. So we're going to want to use the second formula. Change in electric potential energy is equal to Q times change in voltage. So that's going to be Q times voltage final minus voltage initial. Our initial voltage is going to be the one of the plate that the proton is touching at the beginning, which is 0 volts, and our final is going to be the voltage of the plate that the proton will be touching at the end, which is negative 500 volts. And we can fill this in. Our charge for this question is going to be the charge of a proton, which is always equal to 1.6 times 10 to the negative 19 coulombs. And we can multiply that by negative 500, take away 0. And when you plug that into a calculator, you should get negative 8 times 10 to the negative 17 joules. And now we want to figure out how fast it was going. So to solve for that, we can do our change in electric potential energy plus our change in kinetic energy equals 0. So we can rewrite this as energy kinetic final minus energy kinetic initial is equal to our change in electric potential energy. And since we're subtracting this over, it's going to be negative. And we want to be careful with this while writing this out, because our electric potential energy is already a negative number, so that's going to be a double negative, which will turn this into positive. Our kinetic energy at the beginning of the question is equal to 0, so we can just cancel it out. So we can fill this in as 1/2 of mv squared is equal to 8 times 10 to the negative 17. And we want to rearrange this for v, and you want to be careful while doing this that you don't forget any of your variables. So it's going to be 8 times 10 to the negative 17, and we're going to multiply that by 2 to get rid of the 1/2, and then we're going to divide that by the mass of a proton, which is 1.67 times 10 to the negative 27 kilograms, and we can cancel that out. And then we want to square root it to cancel out the square root. And now you want to be careful when plugging this into the calculator, and you might want to do it in steps, because I always get problems doing it like this, and I always also forget square root. So be very careful not to forget the square root. And when you plug that in, you should get 309,529.2. And we're going to put this into significant figures, which is going to be 3.10 times 10 to the 5, And our units for this are going to be meters per second.
In conclusion, we have learned two ways to calculate electric potential energy, as well as how the forces in an electric field act on point charges to help us create electric potential energy. We also learned a bit about how it was discovered, and that nowadays, most people use it every day without even knowing it. Thank you for watching.